it's an object, if that is the size of it, that is 1,000,000 times more massive.
Just weeks ago, astronomers expected our third ever interstellar visitor to quietly slip past Mars and disappear forever. Instead, 3I Atlas did something that broke every rule in the book. In 48 hours, this alien wanderer exploded with 6 times more brightness than any model predicted, building a massive green cloud half the size of the Sun. And that's just the beginning of this cosmic mystery. What's up, space explorers? If you're fascinated by the mysteries lurking in the depths of space, you're going to want to stick around for this one. Today we're diving deep into one of the most mind-bending discoveries, an object from another star system that's rewriting everything we thought we knew about interstellar visitors. Meet 3I Atlas, and that weird designation actually tells an amazing story. The 3I means this is only the third interstellar object we've ever detected. The first was the mysterious Oumuamua in 2017. The second was Comet Borisov in 2019. And now we have Atlas, discovered by the Asteroid Terrestrial Impact Last Alert System. But here's where things get absolutely wild. While those first 2 visitors were strange but relatively predictable, Atlas decided to become the cosmic equivalent of a fireworks show that nobody ordered. And I'm talking about a display that's visible from hundreds of millions of kilometers away. Before we unpack this interstellar mystery that's still unfolding as we speak, smash that subscribe button and hit notifications. What you're about to hear involves breaking science, international space agencies scrambling to reprogram their spacecraft, and discoveries that could change how we understand our place in the galaxy. Picture this: it's January 2025, and astronomers worldwide are casually tracking 3I Atlas as it approaches its closest point to Mars. Based on every model we have, this interstellar comet should be getting slightly brighter as solar heating increases, but nothing dramatic, just another cosmic wanderer doing predictable comet things. Then, over 48 hours in mid-January, everything went haywire. The comet didn't just brighten, it detonated with luminosity. We're talking about a 6-fold increase in brightness that had observatory networks lighting up with emergency alerts faster than you could say, "What the hell is happening out there?" Let me put these numbers in perspective for you. Atlas jumped from magnitude 16, barely visible even with decent amateur telescopes, to magnitude 12 in less than 2 days. For those not familiar with astronomical magnitudes, this logarithmic scale means the comet became roughly 40 times brighter. Imagine if your phone's flashlight suddenly became as bright as a car's headlight, except this is happening to an object twice as far from the Sun as Earth is. But here's what makes this truly unprecedented. This explosion happened at 2 astronomical units from the Sun. At that distance, comets are supposed to be relatively quiet. Solar heating should be moderate, outgassing should be gentle, and brightness changes should be gradual. Atlas basically said, "Hold my beer," and rewrote the physics textbook. The first alerts came from amateur astronomers in Australia, and this is why citizen science is so crucial. Professional observatories often have rigid schedules planned months in advance, but dedicated amateurs can respond to sudden changes immediately. By the time major observatories confirmed the readings, social media was already buzzing with telescope images showing this impossible brightening event. Within 24 hours, observatories on 6 continents were redirecting their instruments toward Atlas, cancelling scheduled observations to focus on this developing cosmic crisis. Because make no mistake, when an interstellar object starts behaving this erratically, it becomes a scientific emergency. If the brightness surge wasn't mind-bending enough, Atlas decided to show off its alien origins with the most spectacular light show in recent astronomical history. This thing turned green, not a subtle tint, but a brilliant, almost neon green that dominated every photograph and made it look more like a cosmic rave than a natural object. The coma, the cloud of gas and dust surrounding the nucleus, expanded to over 650,000 kilometers across. That's roughly 51 times the diameter of Earth, or about half the diameter of our Sun. We're looking at a structure so vast that light takes over 2 seconds to cross from one side to the other. Enter the James Webb Space Telescope with data that changed everything. JWST's January 2025 observations revealed a carbon dioxide to water ratio of 8.2, even higher than initial estimates. This is absolutely off the charts compared to solar system comets, where water usually dominates by huge margins. The breakthrough came when researchers realized they were looking at a completely different type of chemistry. The brilliant green wasn't from carbon at all. It was atomic oxygen emission at 5,577 angstroms. Solar ultraviolet radiation was ripping apart those abundant CO2 molecules, creating excited oxygen atoms that emit green photons as they return to lower energy states. This discovery is profound because it's essentially alien chemistry broadcasting itself in visible light. The extreme CO2 content tells us Atlas formed in a completely different stellar environment, probably around a star with different temperature, composition, or evolutionary history than our Sun. We're literally watching chemistry from another corner of the galaxy putting on a light show in our solar system. Let's talk about just how insanely fast this cosmic visitor is moving, because the numbers are honestly difficult for human brains to process. As of March 2025, Atlas is screaming through space at nearly 68 kilometers per second. That's more than double the orbital velocity of Mercury, our solar system's speed demon. To give you some perspective on this velocity, Atlas could travel from Earth to the Moon in 65 minutes. The Apollo astronauts took 3 full days for that same journey. If you could somehow hitch a ride on this comet, you could fly from New York to Los Angeles in about 30 seconds. This extreme speed confirms what orbital mechanics told us from day one. Atlas is following a hyperbolic trajectory with an eccentricity greater than 1. In plain English, this means it's not gravitationally bound to our Sun. This is a one-time visitor making a single pass through our solar system before vanishing into interstellar space forever. The physics behind this speed is elegantly simple yet mind-blowing. Atlas is essentially falling toward the Sun under gravitational acceleration, but because it started from such an incredible distance, possibly light years away, it has enough kinetic energy to escape our Sun's gravitational well after its close approach. For comparison, NASA's Parker Solar Probe will eventually reach about 200 kilometers per second, but only after years of carefully planned gravity assists and precise orbital mechanics. Atlas achieves nearly 70 kilometers simply by falling through space under the natural pull of gravity. It's like nature's own particle accelerator on a cosmic scale. The timing of Atlas's Mars flyby in early 2025 created an unprecedented opportunity. Just as Earth-based telescopes began losing the comet to solar glare, it passed within 28 million kilometers of Mars, close enough for the red planet's fleet of orbiters to take over observation duties. It's like a perfectly choreographed handoff in the ultimate relay race. When Atlas began its impossible brightness surge in January 2025, it triggered what can only be described as the largest coordinated astronomical emergency response in history. Observatory schedulers from Hawaii to Chile found themselves in a desperate race against solar geometry and time itself. The enemy was solar elongation, the shrinking angle between the comet and the Sun as seen from Earth. Every day that passed meant Atlas was getting closer to being lost in solar glare, with the critical 30-degree threshold approaching fast. Below that angle, even the most powerful ground-based telescopes become nearly useless. The Hubble Space Telescope, already overbooked with observations planned years in advance, activated rarely used emergency protocols. Target of opportunity observations were approved within hours instead of the usual months-long process. HST captured ultraviolet and optical images as the coma continued its explosive expansion, with instrument teams working around the clock to avoid saturation from the rapidly brightening target. The James Webb Space Telescope secured emergency observation time that required approval from the highest levels of NASA. JWST's mid-infrared spectrographs locked onto the comet's core, revealing chemical signatures unlike anything seen in our solar system. The CO2 detections were so strong they initially seemed like instrument errors until multiple confirmations proved them real. Meanwhile, the global network of ground-based observatories went into overdrive. The Gemini Observatory in Chile grabbed rapid sequence imaging to track structural changes in the coma. The Very Large Telescope Array provided complementary spectroscopy. Radio telescopes searched for molecular emissions. Even amateur astronomers with sophisticated equipment contributed crucial data points. The coordination was unlike anything seen before in astronomy. Private Slack channels, encrypted data transfers, and 24/7 video conferences connected researchers across time zones. Raw observations were shared within minutes of capture, with preliminary analyses circulating faster than traditional peer review could handle. The race was against an unforgiving deadline. By early February 2025, solar elongation would drop below the critical threshold, making ATLAS invisible to Earth-based instruments just as it approached its most scientifically interesting phase. As Earth's telescopes went blind, Mars transformed into humanity's most crucial observatory. The Red Planet hosts an impressive international fleet of robotic explorers, each suddenly tasked with tracking an interstellar visitor that was never part of their mission plans. But here's the challenge. These spacecraft were built to study Mars, not hunt comets. Asking them to track a fast-moving interstellar object is like repurposing a microscope to work as a telescope, while following a race car from a helicopter. NASA's Mars Reconnaissance Orbiter carries HiRISE, the high-resolution imaging science experiment, capable of resolving objects as small as a desk on the Martian surface. The question was whether this incredible resolution could spot Atlas's nucleus, buried inside its massive, expanding coma. The engineering challenges were immense. HiRISE had to track an object moving at 65+ kilometers per second while avoiding any risk of pointing toward the sun, which could permanently damage the camera's sensitive detectors. Teams at the University of Arizona worked frantically to develop new pointing algorithms and safety protocols. The European Space Agency's Mars Express, operating since 2003, brought the high-resolution stereo camera to the hunt. HRSC's wide-field capabilities were perfect for capturing the comet's full structure, while its multiple color filters could separate dust from gas in the expanding coma. What made this even more impressive was the international coordination required. European mission controllers had to synchronize with NASA operations, sharing orbital predictions and coordinating observation windows to maximize scientific return while ensuring spacecraft safety. The ExoMars Trace Gas Orbiter contributed SASIS imaging and NOMAD spectrometry, instruments designed to detect trace gases in Mars's atmosphere. NOMAD's sensitivity to CO2, water vapor, and organic molecules made it perfect for confirming JWST's findings about the comet's exotic chemistry from a completely different perspective. Just when scientists thought ATLAS couldn't break any more rules of physics, it revealed its most impossible feature yet, an anti-tail pointing directly toward the sun. If you know anything about comets, you know this should be impossible. Comet tails point away from the sun, blown outward by solar wind and radiation pressure, always without exception. ATLAS apparently didn't get that memo. This wasn't a photographic illusion or processing artifact. Multiple independent observations from Hubble, ground-based telescopes and Mars orbiters all confirm the same thing. A distinct stream of material extending from the comet directly toward our star, visible across hundreds of thousands of kilometers of space. The usual explanation involves geometric projection effects. Sometimes when Earth crosses a comet's orbital plane, older tail material can appear to point sunward due to perspective tricks. But ATLAS's orbital geometry didn't fit this explanation at all. Teams of plasma physicists and dynamics experts dove into the data to solve this puzzle. Their conclusion was startling. The anti-tail represents real physical material, massive dust grains being launched directly toward the sun by asymmetric jets erupting from the nucleus. We're not talking about tiny particles easily pushed around by solar radiation. These are grains at least 15 to 20 microns across, heavy enough to resist solar wind pressure and maintain their sunward trajectory against all the forces trying to blow them away from the sun. But how do these grains survive the intense solar heating that should vaporize them instantly? The answer lies in their composition and the unique chemistry of ATLAS. These particles appear to be mixtures of carbon dioxide ice and darker, more refractory materials, probably carbon-rich compounds that can endure solar radiation long enough to create the observed anti-tail. Computer models suggest these grains are blasted from hyperactive regions on the sunward hemisphere of the nucleus, where solar heating creates intense jets of sublimating material. The strongest outbursts create a snow line that extends much farther toward the sun than in typical comets, allowing larger particles to survive the journey. The story gets even more complex when electromagnetic forces enter the picture. As the coma expands, it becomes a natural plasma physics laboratory. Charged dust grains interact with both the solar wind and the comet's own magnetic field, creating narrow streams and spikes that further sculpt the anti-tail structure. Some researchers initially speculated about more exotic explanations: artificial structures, self-organizing plasma, even engineered materials. But detailed analysis showed every feature fits within known physics, just pushed to absolute extremes by the comet's unique chemistry and unprecedented activity levels. In late February 2025, Atlas reached the most critical phase of its journey, perihelion, its closest approach to the Sun. Moving at nearly 68 kilometers per second, the comet passed within 1.35 astronomical units of our star, closer than Mars's average distance, but still far enough to avoid complete destruction. This timing created both the greatest scientific opportunity and the greatest frustration. Perihelion should be when Atlas reached maximum activity, potentially revealing new aspects of its alien chemistry. But from Earth's perspective, the comet was completely lost in solar glare, invisible even to our most powerful telescopes. With no direct observations possible, scientists developed three competing scenarios for what might happen to Atlas during its solar encounter. Scenario 1. Gradual fade. If the nucleus was relatively solid with a finite supply of volatile ices, perihelion would slowly exhaust the most active materials. The comet would dim steadily as carbon dioxide and other compounds were depleted, leaving behind a dark, inert core. Scenario 2. Catastrophic breakup. The extreme outgassing and rapid brightness changes suggested a very porous, loosely bound structure. Solar heating at perihelion could trigger complete disintegration, scattering fragments that would briefly flare before fading to invisibility. Scenario 3. The ultimate surprise. If deep layers of pristine CO2 ice were suddenly exposed to solar radiation, Atlas could produce another dramatic brightness surge. The green glow might intensify rather than fade, creating the most chemically active interstellar object ever observed. Each outcome would teach us fundamentally different things about interstellar wanderers. A gentle fade would suggest these ancient objects are surprisingly durable, capable of surviving millions of years in the cosmic deep freeze. Fragmentation would indicate they're more fragile than expected. Another flare would reveal hidden complexity in their internal structure. The implications reached far beyond one comet. Atlas represents a direct probe from another stellar system, carrying physics and chemistry from a completely different cosmic environment. Its behavior would calibrate our models for future interstellar visitors, some of which might pose actual threats to Earth. In early March 2025, after weeks of agonizing waiting, Atlas finally began emerging from the Sun's overwhelming glare. Ground-based telescopes could once again point toward the comet's position without risking detector damage from scattered sunlight. The first observations were tense affairs conducted by Southern Hemisphere observatories, where the comet was best positioned after perihelion. Amateur astronomers with small but well-equipped telescopes were often first to spot the returning visitor, since they could observe under darker skies without the scheduling constraints of major facilities. The initial reports were encouraging. Atlas had survived. The nucleus remained intact rather than fragmenting into debris scattered across space. However, the comet was clearly changed by its solar encounter. The overall brightness had decreased significantly from the dramatic January surge, suggesting substantial loss of volatile materials. But remarkably, the alien green glow persisted. Follow-up spectroscopy from JWST and ground-based facilities confirmed ongoing carbon dioxide emission, though at reduced levels compared to the pre-perihelion explosion. The exotic chemistry that made Atlas so unique had survived its close encounter with our Sun. Hubble imaging revealed a coma that was noticeably smaller but more structured than before perihelion. New jets and streamers were visible, suggesting that solar heating had exposed fresh areas of the nucleus to direct sunlight. The anti-tail phenomenon persisted but appeared more diffuse. As of late March 2025, ATLAS is following a brightness decline pattern most consistent with gradual volatile depletion rather than catastrophic material loss. This suggests a nucleus that, while highly active, maintains structural integrity under intense solar heating. However, the persistence of CO2 emission indicates substantial reserves of carbon dioxide ice remain in deeper layers. This raises the possibility of future brightness fluctuations as the comet's rotation continues to expose different surface regions to sunlight. The 2025 ATLAS observation campaign has generated the most comprehensive dataset ever collected for an interstellar object. 19 countries, 27 telescopes, and 6 Mars orbiters contributed observations spanning 5 months of continuous monitoring. The chemical analysis alone represents a revolution in our understanding of interstellar objects. The CO2-to-water ratio of 8.2 is completely unprecedented among solar system comets, where water ice typically dominates by huge margins. This extreme composition points to formation around a very different type of star than our Sun. But the real breakthrough came from isotope analysis using the most sensitive spectrographs available. The ratios of carbon-12 to carbon-13 and oxygen-16 to oxygen-18 in ATLAS don't match patterns seen anywhere in our solar system. This provides direct, unambiguous evidence of its extrasolar origin and reveals details about the stellar environment where it formed billions of years ago. These isotope signatures suggest ATLAS formed in a system with a carbon-rich star, possibly an evolved red giant that enriched its surrounding disk with carbon compounds through stellar winds. The specific ratios indicate formation temperatures and chemical conditions completely unlike those in our solar nebula 4.6 billion years ago. Lessons learned from the ATLAS campaign are driving improvements in astronomical infrastructure. Better coordination protocols, more sensitive detection systems, and rapid response observation networks are being developed specifically for transient interstellar phenomena. Future campaigns will benefit from pre-positioned instruments, standardized data formats, and automated analysis pipelines that can extract scientific results in real time rather than months after observations are complete. ATLAS has essentially founded a new scientific discipline, interstellar archaeology. By studying visitors from other stellar systems, we can learn about cosmic environments that are too distant for direct observation. Each object becomes a time capsule carrying information about its birth system. Future observations of many such objects could map the chemical evolution of our galactic neighborhood, tracking how stellar populations have changed over billions of years. We might even identify objects from stellar systems that no longer exist. The astrobiology implications of interstellar objects like ATLAS are profound. If life can survive interstellar travel aboard comets, then biological information might be exchanged between stellar systems on a regular basis. The galaxy could be far more biologically connected than we've assumed. Future interstellar visitors might carry organic compounds or even preserve microorganisms that could reveal how life emerges and evolves in different stellar environments. ATLAS has shown that these objects preserve chemical information across vast distances and time spans.